Okay. I'd like to thank the organizers for inviting me. I always enjoy coming to this beautiful place. Very nice to be here again. So this probably has a little bit less connection with entanglement than most of the talks at this conference, I must admit. Maybe I'll mention some as I go along. So this is some work I did with actually two former postdocs at UBC. Armin Romani, who's moved, he's now a faculty member at Western Washington University, and Dima Pekulin now works at Microsoft Station Q. I'm having a terrible time switching slides here for some reason. There we go. So here's an outline of my talk. I'm going to give some, first of all, give some motivation, actually some experimental motivation for this model that we're studying. Talk about our predicted phase diagram, which involves several phase transitions, and I'll talk about a field theory normalization group approach and the nature of the critical points, and then come to some conclusions. I'll probably also touch on, so this is mainly about the two-dimensional case, so I'll probably touch briefly on the one-dimensional case that we studied several years ago and understand much better than the one-dimensional case. So well, everybody here I'm sure knows that Majorana fermions are proposed in high energy physics, but I guess there's no evidence that they exist yet. And the corresponding operators are Hermitian, so that distinguishes them from usual fermionic creation and annihilation operators. And they've apparently been observed in condensed matter physics, although it still remains a bit controversial. And they're candidates for qubits, and in fact they're the main focus of Microsoft Station Q research, trying to make qubits out of Majorana fermions. Shoot. So the first experiments that claim to see Majorana fermions were published, I think, in 2012 by the Calvenhoven group in Delft, and two other groups got similar results. So these could occur, in this case you just get two Majorana fermions. I'm going to talk about a lot more than two. So if you put a quantum wire on top of an ordinary superconductor, and the quantum wire has to have strong spin-orbit interactions, and you apply a magnetic field, the quantum wire gets a proximity-induced superconductivity and can go into a topological superconducting phase. And then it's predicted that two Majorana modes exist at the two ends, well, at the two ends of the superconductor where the wire runs off the end of the superconductor. So if we write down a low-energy Hamiltonian, it's extremely simple. So we expect a gap in the superconductor except for these two Majorana modes. In general, there will be gapless states in the quantum wire, in the normal part of the quantum wires, and they could have interesting interactions with the Majorana fermions, but if we ignore those for simplicity, then we only have these two Majorana modes, gamma 1, gamma 2. We can combine them into this simple Hamiltonian, and this tunneling parameter t is expected to be very small. It goes to zero exponentially with the length of the quantum wire. So these Majorana fermion operators are Hermitian, and they obey these anti-commutation relations, and in particular gamma squared is 1. So we can combine two Majorana fermions to make an ordinary Dirac fermion, and then this Hamiltonian takes this form. So there are two states where the energy level is either filled or empty, and these are sometimes called Schrodinger cat states because they exist simultaneously at both ends of the quantum wire, so that they can be extended over a very large distance. And these two states are a potential qubit. Yeah. So now I want to talk about having a much larger number of Majorana fermions. And this was proposed in this situation. So if we have a strong topological insulator, and then we have a thin layer of superconductor on top, the magnetic field, so we get a vortex lattice, it's predicted that a Majorana fermion will exist at the core of every vortex. This is somewhat related to what I was discussing before. So the Majoranas tend to occur at the interface between a superconducting and normal region, and we can think of a vortex as having that feature. So this presents a kind of interesting model. This has not yet been observed experimentally, but actually a couple of experimentalists in Canada are attempting to observe this. And now we have a macroscopic number of Majorana fermions, and we could attempt to understand their behavior. Basically, we have sort of a lattice, and these Majorana operators exist on these lattice points. They could hop around on the lattice. They could also have interaction terms. Okay, I think it keeps trying to connect me to EduRoom. That's a problem. Okay, so we've studied the simplest possible version of this model with the shortest possible range interactions, and we call this the Majorana-Hubbard model. I'm going to talk about its phase diagram, or our proposal for its phase diagram on the square lattice. We're also looking at the triangular lattice case. So most vortex lattices are triangular, but there are a few materials that have square vortex lattices. The interactions are expected to drop off exponentially, so it might be reasonable to include just the shortest range interactions we could write down. So this is the Hamiltonian we studied. So we have a nearest neighbor hopping term on a square lattice. We have the shortest possible range interaction term we could write down. This necessarily involves 4 lattice sites. And the reason is that, well, a square of 2 Majoranas is 1. So if you put a product of 2 Majoranas in one lattice site, you don't get anything quantum, you just get the identity operator. So the shortest range interaction we can write down must involve 4 lattice sites. So it involves a plaquette on the lattice. This minus sign comes in, this was argued for a long time ago, based on the fact that we should have 1 flux quantum per plaquette, and this actually dictates the signs. We can also have a second neighbor hopping term, and this actually changes the phase diagram quite a bit, as I'll be discussing, because it actually breaks time reversal. And again, the signs are constrained by this flux condition. And also, somewhat confusingly, it turns out that positive G actually corresponds to attractive interactions and negative G to repulsive interactions. This has to do with the factor of I that we saw before. If we convert a couple of Majoranas into a Dirac, we get a factor of I coming in. So we get 2 factors of I, which gives us a minus sign. So this is a kind of interesting model to study, and it presents some serious challenges. It's probably a similar level of difficulty to the 2-dimensional Hubbard model, and people have been trying to solve the 2-dimensional Hubbard model for the last 30 or 40 years at least, with probably some success, but it's been a great challenge. And this model has most of the same kinds of difficulties. So there's a Monte Carlo sign problem if you try to do quantum Monte Carlo. In some ways it's more difficult perhaps because there's no U1 symmetry here, no conserved charge. Other hand, there's no chemical potential we can add, so that maybe simplifies the phase diagram because we have 1 fewer parameter to adjust. So the 1-dimensional case we solved several years ago with Marcel Franz and Armin Rouhani and a visiting student, Xiaoyu Zhu. And the 1-dimensional case, we could solve it using density matrix renormalization group, although this is quite challenging, and analytic methods. 2-dimensional case, we're currently studying ladders numerically using DMRG methods. And we've also, sort of emboldened by what we understood about the 1-dimensional case, we've proposed a phase diagram based largely on mean field and field theory arguments and renormalization group. And we've ignored all kinds of other things that we could have included, which include disorder or possibly a distortion of the lattice. Maybe the lattice might distort in some way to lower the energy, some sort of Pyros type distortion, could be disorder. So lots of other features could be added to this model. So a very important and interesting point about this model is that in principle the hopping terms can be tuned to 0 by adjusting a gate voltage on the topological insulator. So if the topological insulator is thin enough that we can adjust its chemical potential with a gate voltage, then it's proposed that there's a special symmetric value of the chemical potential where the hopping terms are 0 by symmetry. So we could define dimensionless interaction strength as a ratio of G over T, and this would go to infinity at this critical point. So this makes the phase diagram as a function of G over T accessible in principle with experiments. And as I mentioned, T2 breaks time reversal and changes things considerably. So this is a schematic phase diagram that we proposed. So there's a gapless phase if the coupling is weak enough, and this is basically, as we'll see, because the interactions are irrelevant. So we can map this into a field theory at low energies, relativistic field theory, actually in 2 + 1 dimensions, and the interactions are irrelevant. But if they get strong enough, nonetheless, they can lead to phase transitions. The phase transition that we think occurs at positive G, which actually corresponds to attractive interactions, is we believe is supersymmetric, and it's a continuous transition. There's also a transition at negative G, which involves spontaneously broken time reversal, This happens if T2 is 0, so there is time reversal. And this is also described by relativistic field theory. And then there seems to be a first-order phase transition at stronger repulsive coupling. And these strong coupling phases involve Majorana pairing, which I'll explain what I mean by that. So it involves sort of entangling of pairs of Majoranas. So there's some interest in studying both sides of the coupling constant because since this effective low energy Hamiltonian is sitting on top of a superconductor and there are effectively attractive interactions in a superconductor, it's not quite clear what sign of the effective interaction we actually might get. So, well, these phase transitions are characterized by spontaneously broken symmetries, and there aren't many symmetries in this Hamiltonian, so you might ask what symmetries are we talking about here? So we actually have the following symmetries. We have translation by one site in the x or y direction. Actually, because the sign hopping term alternates in sign, we have to put in some minus signs into some of the Majorana modes when we translate in the vertical direction, but we can do that. There's also a pi/2 rotation symmetry on the square lattice. And if T2 is 0, we have a time reversal symmetry and also a parity or spatial reflection symmetry. And even if we add T2, we still have the product PT. So these are basically all of the symmetries that the model has. But we can derive a low energy field theory, and this has a number of emergent symmetries, which I'll be discussing. So these the phases of broken translation symmetry are a consequence of the tendency of Majorana modes to pair up to make Dirac fermions. I already discussed that we can combine two Majoranas to make a Dirac fermion, and then we could write the hopping term, for example, looks like this. So if all we had was a hopping term and the Majoranas, well, if we only had if every second pair of Majoranas combined, so each Majorana was only part of one hopping term, then we would have a sort of a trivial Hamiltonian that was just a free, not even any hopping term, actually just basically a chemical potential. And depending on the sign of the hopping term, the band would either be filled or empty. But with a uniform hopping term that we have, this sort of pairing of Majoranas is not possible without breaking translation symmetry. So, for example, we could combine a pair at site M2n with site M2n plus 1, or M2n minus 1 with M2n. But to do that kind of pairing, we necessarily break translation symmetry. So the fact that this spontaneous breaking of translation symmetry occurs has been well established in our work on the one-dimensional model, and we believe it also occurs in the two-dimensional case. These phases also break rotational symmetry and parity or reflection symmetry, which is present when T2 is 0. So here is a possible order parameter. So this is just a product of two Majoranas on a vertical line, nearest neighbors. And actually the A term doesn't break a symmetry, but the B term would break a symmetry. And it corresponds to this sort of picture. So the idea is that the solid lines represent combining pairs of Majoranas to make Dirac fermions. And there's several ways we can do it. We could do it this way or we could do it that way. And the empty circles represent the fact that there's a tendency for, at least at a mean field level, a tendency for this Dirac level to be empty, at least when G is positive. So this is actually what we expect for positive G. And this is what we call the ferromagnetic Majorana phase, just meaning that all of these Dirac levels are tending to be empty. So an important point is the chemical potential cannot be controlled in this model because there's no conserved U1, so it kind of dynamically adjusts itself. So if we try to think in a mean field picture about Majoranas forming Diracs, then the chemical potential will also be a sort of parameter which is determined dynamically in the mean field theory and depends on the coupling constant. Such states actually are fourfold degenerate because, well, we can translate by one side in the vertical direction going from here to here, or we can rotate by pi/2 and instead get Majoranas forming on horizontal bonds. So we get 4 ground states in this case. If G is negative, there's a tendency to get antiferromagnetic pairing. So again, Majoranas can pair up to form Diracs. But now we find that these Dirac levels, at least at a mean field level, tend to alternate empty filled, empty filled. this can be understood because if we just kind of factorize the interaction on plaquettes in a mean field approximation, then we just have a product of basically C dagger C, 2 C dagger C minus 1. So depending on the sign of the interaction, the states, fermion states, will want to be both filled or empty, or one empty and one filled. And the hopping term actually, we take always a positive hopping term, so it will tend to favor empty states. So a negative G favors sort of a charge density wave in this mean field picture, and which is actually repulsive interactions, and attractive interactions for positive G favor this sort of empty band state. In this case, we actually have 8 ground states because we can translate by 1 in the x or y direction, and we can rotate. So we've confirmed that these types of broken states occur in results on both 2-leg and 4-leg ladders, which are actually not yet published. So what about time reversal? Time reversal is a little bit tricky here because the hopping term contains a factor of I, and time reversal takes I to minus I. So to have a time reversal symmetry, we necessarily have to put a minus sign into basically half of the Majorana modes. So if we have only nearest neighbor hopping, we can basically change the sign of the gammas when m plus n is odd, and this remains a symmetry of the nearest neighbor hopping term. But the second neighbor hopping term will not preserve this symmetry because it basically hops between 2 Majoranas, where m plus n has the same sign. So the second neighbor hopping actually breaks time reversal. We don't expect time reversal to be present, presumably because the underlying physical situation involved in a magnetic field, which breaks time reversal. But we might hope that the second neighbor hopping could be relatively small compared to nearest neighbor hopping, and possibly interaction strength, because it does drop off exponentially with separation of the lattice sites. So what we find is that when T2 is 0, we get a phase with spontaneously broken time reversal occurring for repulsive interactions, and we can think about effectively generating a second neighbor hopping dynamically from interaction effects. So this describes all the broken symmetry phases that we expect. So these are a result of doing a simple-minded mean field picture, but they're also consistent with results in 2- and 4-leg ladders. They're consistent with our results in the 1-leg ladder, which has a very interesting phase diagram, which we discussed some time ago, and they arise with mean field theory. But we've been playing around a bit with the mean field theory, and we're not 100% confident of everything I'm saying here. So now let me talk about a field theory approach and the nature of the critical points. So, well, if we just take the non-interacting model, obviously we can solve it exactly. And we get a dispersion relation which looks like this, depending on T and T2. So if T2 is 0, then the energies vanish at two points in K space, actually K equals 0, and also another point which we take to be Ky equals 0 and Kx equals pi. And the Brillouin zone is a bit peculiar here. It only runs over pi in the y direction because of this alternating sign for the hopping term in the y direction. But we actually restrict it, unlike what I wrote here, we restrict Kx to run between 0 and pi. And this has to do with the fact that we're dealing with Majorana fermions. So when we Fourier transform, the Fourier transforms of Majorana fermions are not Hermitian, but we find that gamma minus k is gamma k dagger. So we can actually restrict ourselves to sort of half of the Brillouin zone. So we can restrict ourselves to positive kx. So at low energy, dispersion relation looks like this. So if T2 is 0, we have a massless relativistic dispersion, and if we have a small T2, we have a massive relativistic dispersion. So it's a little bit like graphene, except that at these 2 Dirac points, we probably shouldn't call them Dirac points, maybe Majorana points, we actually have relativistic Majorana modes. And we get 2 component Majorana fermions just because of the broken translation symmetry in the y direction. So we sort of have 2 fermions per unit cell. And this leads to a relativistic 2 component Majorana fermion structure. And because we have 2 valleys, we actually have 2 copies of Majorana fermions, and we can combine them to make a Dirac fermion. And this actually provides a a way around the Nielsen-Ninomiya theorem, which says that it's impossible to get a single Dirac fermion in a two-dimensional lattice model. We actually get a single Dirac fermion here, but at the price of not having an exact UN symmetry. If we start with Majorana modes, we can get this behavior. So the low-energy Lagrangian takes this form. So it just looks like the gamma mu are two-component Dirac matrices, and this just looks like a standard two-component Dirac fermion model. M breaks time reversal. It's only non-zero if T2 is non-zero. And the leading interaction term just looks like psi bar psi squared. So it's interesting to notice that there's a lot of emergent symmetries here. First of all, there's an emergent Lorentz invariance. There's also an emergent U1 symmetry because this Lagrangian actually conserves charge because we only have the psi bars and psis appearing together. So even though we don't have any particle number conservation in the model, if we write down this effect of low energy theory, it actually appears. But there are actually additional terms I hadn't written down that would break the UN symmetry and also break Lorentz invariance. In particular, there are terms involving 4 factors of the psi fields with 2 derivatives. These are very high dimension operators, but they're also generated from the lattice model, and these do break the UN symmetry. So whether or not the UN symmetry actually appears in low energy physics is not completely obvious because there are very high dimension operators present which actually break that symmetry. So actually, even the interaction I wrote down is irrelevant in the renormalization group sense because fermions in 2 + 1 dimensions have dimension 1, and the marginal dimension is 3, and this is a dimension 4 operator. So this tells us immediately that at least if the interactions are weak enough, we're just going to be in the massless relativistic phase. Now we might ask, well, if the interactions get strong enough, maybe there will be a phase transition, and how can we understand what sort of phases we might go into? At least at a mean field level. And it's instructive to actually write this 2 different ways. So psi1 and psi2 are the 2 components of the relativistic Dirac fermion, and we can write it both ways. So if G is positive, then the mean field argument would suggest that maybe psi2, psi1 gets an expectation value, and this is an order parameter which would spontaneously break the UN symmetry. This would be like a superfluid transition. So this UN symmetry is only emergent, but nonetheless we think that it may get spontaneously broken for large enough positive G, and we think that the explicit UN breaking terms may be irrelevant at this phase transition. If G is negative, corresponding to repulsive interactions, then the order parameter is psi bar psi, which is like the mass term, and this breaks time reversal. So the order parameter broken symmetry is time reversal for negative G, and this emergent U1 symmetry for positive G. We think of these broken symmetry phases as I described in terms of these pairing up of Majoranas. So we get this sort of ferromagnetic pairing phase, which corresponds to the broken U1 symmetry, and the antiferromagnetic pairing phase, actually for strong repulsive interactions. So now I want to discuss very briefly the nature of this critical point that we think occurs at positive G. So you might think it might be the conventional superfluid critical point. The conventional superfluid critical point, which could occur in a system of interacting fermions, normally involves a massless complex boson at the critical point, because you can combine psi1, psi2 by Hubbard-Shatanovich transformation to define a complex boson, and that's the order parameter, and that becomes non-zero at the critical point. So in a Ginzburg-Landau theory, that complex boson is massless at the critical point. But if T2 is 0, we also have massless fermions in the unbroken symmetry phase. And at the critical point, we have massless fermions and massless bosons. So we have the order parameter becomes massless, and also the fermions themselves are massless. And this type of critical point has been studied before in lattice models. And it's been argued that it's supersymmetric. So even though the bosons have to be introduced by Hubbard-Shatanovich transformation, no reason why they should have, well, in the relativistic model, they would have the same velocity as the fermions, but they actually don't necessarily in the lattice model. But it's been argued that the velocities become equal at the critical point, and there's kind of an emergent supersymmetry. What's a bit novel about this model is that the U1 symmetry is not exact either. It's also emergent. So this is a rather unusual situation where we're proposing that an emergent U1 symmetry could get spontaneously broken, and the corresponding order critical point we believe is supersymmetric. If we question, yep. We get a complex boson. We do a Hubbard-Shatanovich, so we introduce phi as psi 1, psi 2, and that's a complex order parameter. That's a superfluid order parameter. So it has a charge under the U1 symmetry, and if it has an expectation value, we're spontaneously breaking the U1. So that's what we would expect based on a kind of mean field analysis for attractive interactions. So if we add a T2 term, we give the fermions a mass, then we no longer have any reason to expect supersymmetry, but now we get massless boson, complex boson at the critical point, but not massless fermions. So now we expect this to be in the usual superfluid universality class, usual Ginzburg-Landau superfluid universality class in 2+1 dimensions. For g less than 0 and T2 equals 0, the order parameter is psi bar psi. And again, we expect that if for strong enough interactions, this order parameter can become non-zero. This corresponds to spontaneously generating a second neighbor hopping in the lattice model. This phase transition has also been studied in the field theory community, in particular by the Klebanov group. And this transition is called the Yukawa-Gross-Neveu transition. It's also described by relativistic field theory. So in both cases, people have done epsilon expansions. So we have some predictions for the critical exponents at these critical points, and some of the exponents are actually fixed by supersymmetry in one case. For T2 non-zero, the fermions are massive, so we expect the usual superfluid transition, and this Gross-Neveu-Yukawa transition disappears because we already have a mass term put in by hand, but we expect another first-order transition to this antiferromagnetic Majorana pairing phase. It's strong enough negative G. So some unpublished work with my student Kyle Waymer, we've been trying to check whether it's really valid that these higher dimension U1 breaking terms can be ignored at the supersymmetric critical point. So we've extended the epsilon expansion to include these operators. And indeed, as you might expect, they're very high dimensional operators at weak coupling, and they remain irrelevant at the supersymmetric critical point. So we have reason, therefore, to believe that this really is in this universality class, and also they're irrelevant at the Yukawa Gross-Neveu critical point. So actually, I'm coming towards the end of my talk. Let me just briefly mention the phase diagram that we found in the one-dimensional case. This was work with Marcel Franz and his student. So this phase diagram is not based on mean field theory. This is based on, well, actually, we understood it using mean field theory, but we confirmed it using DMRG methods. And again, we can analyze critical points using field theory techniques. So now we find that the low energy theory looks like actually a relativistic Majorana fermion in one dimension. In this case, it's just a two-component relativistic Majorana. It does not correspond to a Dirac fermion. And the theory is again relativistic. And it's rather remarkable that we have a massless relativistic Majorana fermion as we vary this coupling constant G over T. So we call this the Ising phase because it's well known that the quantum Ising model in one dimension corresponds to a massless relativistic Majorana fermion. Again, we find it large enough G, and now actually it's huge D. It's about G over T of 250 for reasons we don't really understand. We get a transition into a phase where the Majoranas have paired up, this kind of ferromagnetic pairing phase. And actually we find this transition is governed by the tricritical Ising model, which is actually also supersymmetric. And actually the supersymmetry persists for some region beyond the critical point because the only relevant operator which drives this transition actually preserves supersymmetry. So we expect a massive supersymmetric phase here in this region. For negative G, we find, again, at large enough negative G, we find a sort of antiferromagnetic pairing phase where the Majoranas are pairing up to form Diracs. And we again find a kind of intermediate phase. And in this case, the intermediate phase actually corresponds to a Luttinger liquid combined with an Ising model, or basically a sort of decoupled massless Majorana fermion and a Dirac fermion with interactions leading to a Luttinger liquid. So C is 3/2 here, C is 1/2 here, and C is 7/10 this critical point. And again, these phases at strong very strong coupling correspond to Majoranas pairing up to form Diracs. So we find this is a very strong tendency. What Majoranas like to do, they sort of they really like to pair up and form Diracs, and we've established that clearly in one dimension, and we're speculating this also is going to occur in the two-dimensional case. So let me just put up some conclusions. So most importantly, two-dimensional models of interacting Majorana fermions may have experimental realizations in topological insulator superconductor systems. The hopping term can be, in principle, tuned to 0 by adjusting a gate voltage, making the strong coupling phase diagram accessible. And we predict 4 different phases, or only 3 if T2 is non-zero, when we consider both sides of the interaction term. So at weak coupling, we just get basically a free fermion model, which is relativistic. We predict a supersymmetric continuous transition for attractive interactions into this ferromagnetic pairing phase. Strong enough repulsive interactions, we get a first-order transition into an antiferromagnetic pairing phase. And then if T2 is 0, so time reversal is present, we predict spontaneously broken time reversal at some intermediate repulsive interactions. So I'll stop there. Thank you.
So I have a question about the SUSY transition point. So I understand the SUSY is emergent there, but is there some remnant of it on the lattice, or?
Good question. None that we've been able to understand, basically. So I mean, it's quite remarkable because the lattice model only has fermions. Supersymmetry combines fermions and bosons. The bosons are really the order parameter for the breaking the superfluid symmetry. So the bosons are really composite objects formed from the fermions. So I think it's very hard to see any real remnant of the supersymmetry in the lattice model. But I should say that the same thing happens in the one-dimensional case, and there we've clearly established that it is tricriticalizing. And again, it does correspond to bosons sort of dynamically being generated from fermions, in a sense, from pairing.
I mean, it's interesting because it's interesting to try to construct lattice models that have emergent SUSY for other reasons.
Yes. There have been some other lattice models that have been proposed, but those models actually had underlying, the microscopic lattice models had both fermions and bosons. Those models also had UN symmetry. So this model is rather different than the previous ones in that a huge number of symmetries are kind of emergent and not present in the lattice model.
Actually, just to add to this discussion, since I have a slightly different answer to Ian, because we concocted a model more recently after Ian's paper, and it's inspired by where just the 1D case, where you can explicitly see what the lattice supersymmetry generators are. It's actually just not that different from yours, just slightly not a different, slightly different for Fermi term. But there, then, the supersymmetry generators on the lattice are nonlinear in the fermions. So if you wish, it's like psi plus psi psi psi, which has come up in other contexts as well. And there, then, we explicitly showed you can even check that this is the right dimension operator and all that. So it's not exact on the, so it's still emergent, but at least you see what the lattice analog of the generators are.
Right. Actually, I think there was some proposal like that in the relativistic fermionic context way back in the early 80s. I'm trying to remember the author.
Well, Nikolai wrote down this model, but he didn't do the Majorana version.
Yeah, but this was a continuum field theory, not the lattice model.
Okay, no, Nikolai wrote a lattice model,
okay,
but then, I don't know, somehow didn't think about it in the same way we did. So,
Hi. What's the situation with edge modes in these theories, in these different phases?
Okay. The one-dimensional case, we actually, we thought a bit about edge modes. So I think in some cases they can occur. I mean, I guess the simplest version of edge modes is just like what happens in the Kitaev model in one dimension. So actually, if the Majoranas are combining to form pairs, they could sort of do it in such a way. If you have an even number of Majoranas in your model, which we always have, so we have a well-defined Hilbert space, then they could combine it sort of in pairs everywhere, or they might sort of shift over so that there's two uncoupled Majoranas at the edges. I think that dynamically interactions probably tend to favor not having decoupled Majoranas at the edges, but I think if you modify the model enough, you might get into a phase that has some decoupled edge states. And two-dimensional case, I guess there might also be some sort of gapless states on the edges in some of these gap phases. We haven't actually thought about that yet. Good question.
Could you re-emphasize again, so what field theory gives you, if it, what things that you cannot get if you are not working with field theories, and then and because field theory only works when you have a second order phase transition near the second order phase transition, so could you re-emphasize again, so what field theory gives you? Yeah,
so again, you've hit the key points. So the model is massless in this region. So the low energy physics is described by this relativistic, non-interacting massless field theory. Then we have some interactions, and the most relevant interactions, dimension 4 interactions, are Lorentz invariant and conserve U1. And we believe that those are the interactions that are driving these transitions that occur at, so these transitions occur at couplings of order 1, and this transition occurs at even stronger coupling. So this transition, we think, is not described by field theory because we're already into a gap phase here. But because these transitions are occurring out of gapless phases in their second order, and they're presumably driven by the most relevant interactions, which preserve Lorentz invariance and U1 symmetry, therefore the field theory is a very powerful method of studying these transitions.
So it's hard to see this from your last model?
Yeah, I think I think what you have to do is basically write down the low energy version of the lattice model, which I wrote down earlier. So it does involve relativistic fermions with relativistic interactions. And that's the model we can use to study these transitions. So that can be derived straightforwardly from the field theory. We just have to observe that there are 2 points in the Brillouin zone where the energy goes to 0, and the dispersion looks relativistic near those points if T2 is 0 or small.
Okay, any question? Well, if not,
Can you just say a little more about this emergent U1?
Yep.
Do you have more intuition as to where that's coming from?
I think that actually turns out the rotation symmetry is sort of a subgroup of the U1 symmetry, so that's related to rotation by sort of pi over 4. So if you like, a small finite subgroup of the U1 symmetry is present in the lattice model. And again, the reason it emerges is simply because the lowest dimension operators we can write down are actually dimension 6, whereas we have U1 conserving operators dimension 4. And we think at the critical points, these dimension 4 operators become marginal and drive the transition. And we checked by the epsilon expansion that the dimension 6 U1 breaking terms are irrelevant at the critical points.
okay, so we have a coffee break now, but before doing that, let's thank the speaker again.